The Levitating library. Embeddings, intuition. Every word has a position in space. That position isn't random. It's determined by meaning. Apple, banana, pear. They levitate close to each other. Car, engine, tire. In an entirely different corner. King and queen, almost at the same point. And tire lies far away. Very far away. Distance encodes meaning. This isn't a metaphor. This is the mechanism that holds all of modern AI together. Every chatbot, every semantic search engine, every RAG system, it all starts with embeddings. In the previous episode, we ground language into tokens, sequences of numbers that a model can process. Token 4523 is a dead label. It carries no information about what it represents. For a computer, the relationship between the words dog and cat is the same as between dog and astrophysics. Zero meaning, zero relationship, zero understanding. Today, you see how that dead label transforms into a point in a multidimensional space. A point whose position encodes meaning. You'll see why king sits closer to queen than to tire. You'll also see how the model discovered that relationship on its own, without any instructions, by reading billions of sentences. To understand why these words levitate at exactly these positions, we first need to see what the word looks like without embeddings. The desert of zeros, a dead end. Imagine a world where every word gets an address made up of 50,000 positions. The word apple is a 1 at position 450, and zeros everywhere else. 50,000 zeros with a single 1. This is one-hot encoding, the simplest idea for representing words. The first problem is waste. We're processing enormous vectors that are 99.9% zeros. That's a waste of memory and compute on an industrial scale. But that's not even the worst part. The second problem is fundamental. Every one-hot vector is orthogonal to every other. The dot product of any two different words is always zero. Always. No exceptions. This has concrete consequences in practice. For the model, cat is just as unlike dog as it is unlike rocket engine. The cosine of the angle between them, 0. Between dog and cat, 0. Between cat and love, 0. Everything is equally distant from everything else. Zero neighborhood, zero relationship. It's like a map where every city sits on a separate continent. You can't measure the distance between them. Anyone who has built a keyword-based search system recognizes this limitation. A query for car won't find a document containing the word automobile. One-hot encoding has exactly the same defect. Zero understanding of synonyms, zero semantics. One-hot is a dead end. We need a completely different approach, one where words aren't isolated, but arranged in space according to meaning. Compressing meaning. A chord on 768 strings. The solution is elegant. Instead of a vector of 50,000 zeros, a vector of 768 floating point numbers. Each of those numbers isn't 0 or 1. It's a continuous value, 0.023 minus 0.451, 0.993. This is a dense embedding. The key paradigm shift. Individual dimensions no longer represent words. They represent abstract semantic features. Each word is distributed across those dimensions. This is called a distributed representation. The word dog isn't a single one at a single position. It's a unique chord played across hundreds of strings simultaneously. Each string vibrates with a different intensity. Only the combination of those vibrations gives a unique sound, a unique meaning. Here's how it works under the hood. The embedding layer doesn't perform matrix multiplication. It works like a lookup table. A token with identifier 4523 hits the layer, which reaches into row number 4523 of a matrix with dimensions v by d. V is the vocabulary size, d is the vector dimension, and pulls out a ready-made vector. One operation, complexity O of 1, instantaneous. Consider the scale, 617 million parameters. The embedding matrix of GPT-3 has dimensions 50,257 by 12,288. 617 million numbers dedicated exclusively to mapping tokens to vectors. That's more than the entire BERT-based model, which has 110 million parameters in total. The embedding layer alone is larger than an entire other model. We have vectors. We have positions in space. Now, let's see what happens when we look at that space from above. The geometry of sense. Clusters. Words are points in space, so let's see how they arrange themselves. This is the moment when embeddings stop being abstract and become something visible. Apple, banana, pear. They converge toward each other, forming a green cluster of fruits. Car, engine, tire. A red cluster of vehicles in another corner. Joy, sadness, anger. A blue cluster of emotions. 3 distinct groups. Between them, empty space. What's most striking is that nobody instructed the model to form these clusters. Nobody said, apple and banana are fruits, put them next to each other. This self-organization emerges naturally from the very structure of language in the training data. The model read billions of sentences and learned on its own that apple and banana appear in similar contexts. In recipes, with fruits, with food. These shared contexts pull their vectors toward each other. We could label the axis of our simplified visualization. An axis from concrete to abstract. An axis from positive to negative. An axis from animate to inanimate. In reality, not 3 dimensions but 768, or 4096, or 12,288, as in GPT-3. A human can't visualize that. The principle remains the same. Semantic proximity translates to geometric proximity. We see the clusters. Now we need a tool to measure how close 2 words are levitating to each other. Cosine Similarity. The compass. The map exists. Now we need a compass. A tool for measuring distances between points. Intuition would suggest plain Euclidean distance. In natural language processing, however, the standard is cosine similarity. The reason is pragmatic. In high-dimensional spaces, what matters more than vector length is its direction. The word bank used in a short sentence and in a long document may have different signal strength, but it points to the same topic. Cosine similarity ignores length. It measures only the angle between vectors. 2 vectors pointing in the same direction, semantic closeness. At a right angle, no relationship. A result of 1 means identical vectors, 0-degree angle. Synonyms. A result of 0, orthogonal vectors, no relationship whatsoever. A result of -1, opposite directions. Let's see this with concrete numbers. King and queen, high semantic closeness, vectors nearly parallel. King and car, nearly 0, orthogonal, no semantic relationship. The nuance that breaks expectations. Hot and cold sit close to each other. This seems counterintuitive at first. Consider the contexts. Both words appear with the same nouns. Drink, day, weather, water. The model sees these shared contexts and places hot and cold near each other on the map. Antonyms in natural language processing are often neighbors, because linguistically they behave similarly. This space hides something else though. You can perform arithmetic on it. This is the moment that changes everything. Royal arithmetic. King minus man plus woman equals queen. What you're about to hear is the most famous experiment in the history of embeddings. Take the vector king, subtract the vector man, add the vector woman. Result: the point in space closest to the vector queen. Let's break it down step by step. King minus man. What remains is the pure concept of ruler, stripped of gender, the bare essence of royal power. Now add woman. Pure ruler plus woman, a female ruler, queen. Geometrically, the arrow from man to king is parallel to the arrow from woman to queen. The relationship of gender is encoded as a constant displacement vector in space. This is the analogy parallelogram, 4 points connected by parallel arrows. One axis is gender, the other is power. This geometry is consistent. The same displacement vector works for dozens of pairs. Nobody programmed this. The model discovered the relationship on its own by reading billions of sentences. This is Word2Vec, an architecture created by Google in 2013. A shallow neural network trained on a simple task. Given a center word, for example milk, predict the surrounding words: cat, drinks, white. After training ends, we discard the neural network. What interests us are only the weights of the hidden layer. Those become the embeddings. The network, in trying to predict a word's neighborhood, had to learn its meaning. It encoded that meaning geometrically. At the foundation lies a principle whose most famous formulation comes from John Rupert Firth in 1957. You shall know a word by the company it keeps. This is the distributional hypothesis. Words that occur in similar contexts have similar meanings. A simple idea with enormous power. Word2Vec proved that when you give a neural network billions of sentences and one simple task, predict the neighbors, it will discover semantics on its own. It will discover on its own that king and queen are related. It will discover on its own that Paris is the capital of France. It will discover relationships nobody told it about. Word2Vec has one fatal flaw, however. From static to dynamic, contextual embeddings. Word2Vec is a breakthrough. It has one fatal flaw, however. It's static. Every word gets one vector, regardless of context. Take the word bank. The knight rode to the river bank. That's a body of water. The bank lock broke. That's a mechanism. The zipper on the jacket. That's a fastener. 3 completely different meanings. Word2Vec gives them a single shared vector though. An averaged mash of 3 meanings. A point that doesn't sit precisely in any of the correct clusters. This is the problem of polysemy. One word, many meanings. Word2Vec has no answer for it. The solution arrived in 2018. First Elmo, then BERT and GPT. Contextual embeddings. A fundamental change. We no longer map a word from a vocabulary to a vector. We map a word in a specific sentence to a vector. The self-attention mechanism lets the word bank look around at its neighbors in the sentence. If it sees a knight and walls, its vector shifts toward architecture. If it sees a key and a door, toward locksmithing. The same book in the Levitating library changes position depending on the company on the shelf. How self-attention works exactly, that's a topic for a separate episode. Contextual embeddings are the foundation on which all of modern AI stands. That's precisely why your RAG system works or doesn't work. A query about the bank of a river reaches the document about the waterway, not about financial services, because the embedding of that word is different in every context. This is critical. Without contextual embeddings, there would be no semantic search, no chatbots, no AI agents. Summary. Let's recap what we saw on this journey through the Levitating library. Tokens are dead labels. Embeddings turn them into points in space where distance encodes meaning. One-hot encoding is a dead end. 50,000 zeros, zero relationships between words. Dense embeddings compress meaning into hundreds of dimensions, where each dimension encodes an abstract semantic feature. Cosine similarity measures the angle between vectors. It's the gold standard for measuring closeness in natural language processing. Vector arithmetic, king minus man plus woman equals queen, proves that the model discovers hidden relationships from text statistics. Contextual embeddings generate different vectors for the same word depending on the sentence. The end of averaged mush. Embeddings are the map on which all of modern AI stands. Without them, no chatbot, no semantic search engine, no agent can function. In the next episode, the mathematics of this map. If this episode helped you understand embeddings, hit subscribe. The next episode goes deeper into the mathematics. Leave a comment telling us which application of embeddings matters most to you.